Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Alexandre-Théophile Vandermonde's entrance into the world of mathematics possesses a certain dramatic flair, a late-blooming brilliance that underscores the unpredictable nature of genius. At the age of 35, a time when many mathematicians had already established their legacies, Vandermonde embarked on a remarkable intellectual journey, a period of intense creativity that would leave an indelible mark on algebra. This two-year burst of innovation, spanning 87-71 and 87-72, fundamentally reshaped the landscape of algebraic thought, beginning with the sums of 87-71 paper, Memoir sur la résolution des equations. This work addressed a problem that had occupied the minds of mathematicians for centuries: the quest for a general algebraic formula to solve polynomial equations of degree 5 or higher. Generations of brilliant minds had grappled with this challenge, seeking an elegant formula akin to the quadratic formula for second-degree equations or Cardano's formula for cubics. Yet, despite considerable effort, a comparable closed-form solution for higher-degree polynomials remained elusive. Vandermonde, however, approached the problem with a fresh perspective, a shift in thinking that would prove revolutionary. He eschewed the direct pursuit of explicit formulas, a path that had led previous mathematicians to a seemingly insurmountable impasse. Instead, Vandermonde focused on the underlying structure of the solutions themselves, a subtle yet profound alteration of the research program. His approach centered on the properties of functions of the roots of the polynomial equation expressions constructed from these roots. These expressions, now known as Vandermonde resolvents, were central to his innovative methodology. Vandermonde's key insight lay in analyzing how these functions of the roots behaved under permutations of the roots themselves. He meticulously investigated how the values of these resolvents changed when the roots were rearranged, establishing a critical link between the structure of the permutations and the very solvability of the equation. He meticulously constructed expressions that possessed a limited number of distinct values under the action of these permutations, a carefully crafted strategy that connected the algebraic symmetries of the equation to its potential for algebraic solution. Consider, for example, a cubic equation with roots R1, R2, and R3. Vandermonde examined the expression R1 plus omega 2 plus omega 2 R3, where omega represents a complex cube root of unity. He systematically demonstrated how various permutations of the roots R1, R2, and R3 transformed this expression into a small set of related expressions. This systematic exploration was a pivotal step, a concrete demonstration of how the structure of the permutation group of the roots, the set of all possible rearrangements, was intrinsically linked to the nature of the solutions. This work, while independent in its conception and execution, was remarkably contemporaneous with Joseph Louis Lagrange's reflections sur la résolution algebraique des equations, published around the same period. Both Lagrange and Vandermonde, building upon the foundational work of Euler and D'Alembert, were responding to the limitations of existing algebraic techniques and the persistent challenge of higher-degree equations. Their independent yet parallel explorations mark a significant turning point in the history of algebra, a moment of collective intellectual insight. Vandermonde's Memoir sur la résolution des equations served as a crucial precursor to the profound work of Augustin-Louis Cauchy and, most significantly, Évariste Galois. Galois Theory, a cornerstone of modern algebra, is, in essence, the complete fruition of the research program that Vandermonde initiated. Galois' elegant theory provides a definitive criterion for determining the solvability of polynomial equations by analyzing the properties of their permutation groups, a direct descendant of the fundamental concepts Vandermonde introduced in his 1-7+71 paper. The conceptual framework Vandermonde established, the study of functions of roots and their permutation properties, became the foundation upon which Galois would construct his magnificent theory. The influence is undeniable, a direct line of intellectual descent connecting Vandermonde's pioneering work to one of the most significant achievements in the history of algebra. The seeds of Galois theory were sown in the fertile ground of Vandermonde's innovative approach. His legacy lies not only in his specific results, but in the transformative shift in perspective he introduced, a shift that fundamentally altered the course of algebraic research. He provided a new lens through which to view the long-standing problem of polynomial equations, a lens that would eventually lead to the profound insights of Galois. The problem of determining when polynomial equations could be solved by radicals, and, if so, how, had occupied mathematicians for centuries. Vandermonde approached this challenge armed with a novel perspective, one centered on the behavior of the roots themselves. He sought to understand how the roots of a polynomial interacted with each other under permutation, and how those interactions affected the expressibility of the roots in terms of radicals. His insights into the symmetry properties of these functions of roots proved instrumental in the later development of Galois theory. The conceptual framework Vandermonde established, the study of functions of roots and their permutation properties, became the foundation upon which Galois would construct his magnificent theory. The influence is undeniable, a direct line of intellectual descent connecting Vandermonde's pioneering work to one of the most significant achievements in the history of algebra. The seeds of Galois theory were sown in the fertile ground of Vandermonde's innovative approach. His legacy lies in the transformative shift in perspective he introduced, a shift that altered the course of algebraic research. He provided a new viewpoint through which to view the long-standing problem of polynomial equations, a viewpoint that would eventually lead to the profound insights of Galois. Beyond his contributions to the theory of equations, Vandermonde also fundamentally shaped the development of another crucial area of mathematics, the theory of determinants. Vandermonde's 1-7-72 paper, Memoir sur l'elimination, marks a watershed moment in the history of determinants. Prior to this work, determinants existed primarily as computational tools, ad hoc recipes for solving systems of linear equations. They lacked a systematic theory, a conceptual framework that would elevate them from mere instruments into mathematical objects worthy of study in their own right. Vandermonde's contribution was to provide precisely that, the first systematic, abstract theory of determinants. He transformed determinants from tools into objects. The primary challenge Vandermonde addressed was the absence of a general, symbolic, and recursive theory for what we now call determinants. Methods like Cramer's rule, while effective for solving linear systems, were viewed as isolated techniques, lacking a unifying principle. There was no overarching structure, no way to understand determinants as independent mathematical entities with properties that could be explored independently of their application to solving equations. Vandermonde sought to remedy this deficiency to build a foundation for a deeper understanding of these objects. Vandermonde's approach was revolutionary. He treated determinants as objects in their own right, independent of the linear systems from which they arose. He introduced a novel and powerful two-line notation for indices, designed to track terms and their signs algorithmically. This notation, while appearing cumbersome by modern standards, was a crucial step toward abstracting the concept of a determinant away from specific numerical calculations. Consider, for instance, his notation alpha beta/12. In modern terms, this represents the 2x2 determinant term a sub 2, b sub 1, minus a sub 1, b sub 2. The Greek letters alpha and beta denote the rows, while the numbers 1 and 2 denote the columns. The arrangement alpha beta above 12 signifies a specific permutation of the indices, and the sign of the term is determined by whether that permutation is even or odd. This seemingly simple notation allowed Vandermonde to express determinants in a purely symbolic way, freeing them from the constraints of numerical computation. More significantly, Vandermonde gave the first explicit statement of the cofactor expansion theorem. This theorem defines a determinant of size n recursively in terms of determinants of size n-1. This recursive definition is fundamental to the modern axiomatic foundation of the subject. It allows one to break down a large determinant into smaller, more manageable pieces, making computations feasible and revealing the underlying structure of the determinant. Vandermonde's formulation, while presented in the language of his time, is readily recognizable as the cofactor expansion we teach to students today. It involves expanding along a row or column, taking the product of each element with its corresponding cofactor, assigned minor determinant, and summing the results. This process reduces the calculation of an n by n determinant to the calculation of n determinants of size n-1 by n-1, and so on, until one arrives at 2 by 2 determinants, which are easily computed. This recursive structure is at the heart of the theory of determinants, and Vandermonde was the first to articulate it clearly. His notation, such as alpha beta/12 for the 2x2 determinant term a sub 2, b sub 1, minus a sub 1, b sub 2, and his formal rule for the expansion along the first row and column, provided a method that generalized the calculation to any dimension in a way previous sign rules could not. Vandermonde's approach offered a systematic way to compute determinants of arbitrary size. Prior to his work, rules for calculating determinants, such as Saras's rule for 3x3 determinants, were limited to specific dimensions. Vandermonde's cofactor expansion, by contrast, provided a universal algorithm applicable to determinants of any size. This was a major advance, allowing mathematicians to work with determinants in a far more general and flexible manner. Vandermonde's work on determinants directly influenced the subsequent, more comprehensive treatments of determinants by Auguste de Louis Cauchy and Pierre-Simon Laplace. Cauchy, in particular, built upon the formal, recursive framework Vandermonde had created, providing a more rigorous and abstract definition of determinants in terms of the symmetric group. Laplace also developed and extended Vandermonde's cofactor expansion, providing a more streamlined and efficient method for computing determinants. These later developments solidified Vandermonde's initial insights, establishing determinants as a central concept in linear algebra and paving the way for their applications in a wide range of mathematical fields. Vandermonde's work systematized and abstracted the methods of elimination theory developed by Etienne Bezout and Gabriel Cramer. Bezout had developed methods for eliminating variables from systems of polynomial equations, and Cramer had provided a rule for solving systems of linear equations using determinants. Vandermonde took these existing techniques and generalized them, placing them within a broader theoretical framework. He recognized the underlying structure of determinants and their connection to the problem of elimination, providing a more abstract and powerful approach to these problems. The cofactor expansion he formulated remains a cornerstone of every introductory linear algebra course. Students today learn the same basic principles that Vandermonde first articulated over 2 centuries ago. His symbolic, index-based approach paved the way for Cauchy's more formal definition involving the symmetric group, and thus underpins the entire modern theory of determinants. The impact of Vandermonde's work is undeniable. He transformed determinants from computational tools into mathematical objects, providing the foundation for their modern theory and applications. His ambition to create a method of analysis for positional and combinatorial puzzles, like the knight's tour on a chessboard, propelled him to develop a formal mathematical language. This language abstracted the problem from pure geometry into a study of paths and connectivity, a core idea of topology and graph theory. He sought a calculus of positions to analyze movement and arrangement. The cofactor expansion he formulated remains a cornerstone of every introductory linear algebra course. Students today learn the same basic principles that Vandermonde first articulated over 2 centuries ago. His symbolic, index-based approach paved the way for Cauchy's more formal definition involving the symmetric group, and thus underpins the entire modern theory of determinants. The impact of Vandermonde's work is undeniable. He transformed determinants from computational tools into mathematical objects, providing the foundation for their modern theory and applications. Beyond the realm of algebra, Vandermonde's intellectual curiosity extended to problems of position and arrangement. His ambition to create a method of analysis for positional and combinatorial puzzles, like the knight's tour on a chessboard, propelled him to develop a formal mathematical language. This language abstracted the problem from pure geometry into a study of paths and connectivity, a core idea of topology and graph theory. He sought a calculus of positions to analyze movement and arrangement. Vandermonde's 771 paper remarks Sir Les Problems de Situation stands as a testament to his innovative thinking. At the time, puzzles such as the knight's tour were considered recreational diversions, lacking a place within the established framework of mathematical inquiry. The analysis of positional and combinatorial problems lacked a formal mathematical language. These were seen as recreational curiosities rather than objects of serious analytical study. Vandermonde's paper marked an early attempt to create what he termed analysis situs, an analysis of position. He developed a symbolic, algebraic notation to represent the squares of the board and the knight's moves between them. This abstraction shifted the focus from pure geometry to the study of paths and connectivity, a core concept in both topology and graph theory. The knight's tour, a puzzle challenging one to find a sequence of knights moves that visits each square of a chessboard exactly briefly once served as a focal point for Vandermonde's investigations. He formalized this problem by representing the chessboard as a set of locations and the knight's move as a transformation of coordinates. For instance, a move could be represented as transforming a coordinate pair x, y into x plus or minus a, y plus or minus b. By analyzing the sequence of these symbolic transformations, Vandermonde effectively treated the chessboard as a graph and the knight's tour as a Hamiltonian path. This approach predates the formal development of graph theory terminology by several decades. He envisioned a calculus of positions capable of analyzing movement and arrangement, a vision that resonates strongly with modern topological thinking. Vandermonde's work on the knight's tour provides a specific illustration of his general methodology. He sought to move beyond merely finding solutions to individual puzzles. He aimed to develop a systematic approach applicable to a broader class of problems. His symbolic representation of the board and the knight's moves allowed him to analyze the problem algebraically, focusing on the relationships between the squares rather than their specific geometric locations. This emphasis on relationships and connectivity is a hallmark of topological thinking. The modern relevance of Vandermonde's remarks serve less problems to situation lies in its clear intellectual ancestry to modern graph theory and algebraic topology. His ambition to create a non-metric, purely positional geometry directly foreshadows the work of Gauss, Listing, and ultimately Poincaré's creation of topology as a formal discipline. While Vandermonde did not single-handedly invent topology or graph theory, his paper represents a crucial step in their conceptual development. He demonstrated the potential of applying algebraic methods to problems of position and arrangement, paving the way for future mathematicians to develop these ideas further. Vandermonde's work was explicitly influenced by the philosophical program of Gottfried Wilhelm Leibniz, who had called for a geometria cis over a century earlier. Leibniz envisioned a geometry that focused on the relationships between objects rather than their specific measurements or coordinates. Vandermonde's analysis of this can be seen as an attempt to realize Leibniz's vision. He sought to create a mathematical framework for analyzing spatial relationships independently of metric considerations. Additionally, Vandermonde was working in a context where Euler had recently solved the seven bridges of Königsberg problem, another foundational problem of graph theory. Euler's solution, which focused on the connectivity of the bridges and landmasses rather than their geometric shapes, demonstrated the power of topological thinking. Vandermonde likely drew inspiration from Euler's work, recognizing the potential of applying similar ideas to other problems of position and arrangement. Tracing the direct person-to-person influence of Vandermonde's paper is challenging. Its significance lies primarily in its conceptual contribution to the history of topology. It helped solidify analysis as a viable mathematical pursuit, influencing the intellectual climate in which Gauss and others would later develop these ideas. While there is no direct evidence that Gauss, Listing, or Poincaré explicitly studied Vandermonde's paper, it is reasonable to assume that they were aware of his work and that it contributed to their understanding of the field. Vandermonde's paper serves as a reminder that mathematical progress often occurs incrementally, with each generation building upon the ideas of its predecessors. His contribution, though perhaps not as widely recognized as those of later mathematicians, played a vital role in shaping the development of topology and graph theory. Vandermonde's approach to the knight's tour exemplifies the shift from specific problem solving to the development of general analytical tools. Rather than merely seeking a single solution, he developed a symbolic notation that could be applied to a variety of similar problems. This emphasis on generality is a hallmark of modern mathematics. Mathematicians strive to develop theories and methods that can be applied to a wide range of situations, rather than focusing solely on individual cases. Vandermonde's work reflects this broader trend in mathematical thinking. Consider the problem of map coloring, a classic problem in graph theory that asks how many colors are needed to color a map so that no two adjacent regions have the same color. This problem, which seems initially unrelated to the knight's tour, can be analyzed using similar topological techniques. The map can be represented as a graph, with regions as vertices and adjacency relationships as edges. The problem of coloring the map then becomes equivalent to the problem of coloring the vertices of the graph so that no two adjacent vertices have the same color. Vandermonde's emphasis on representing spatial relationships algebraically paved the way for the development of such graph-theoretic approaches to map coloring and other problems. His contribution to the development of mathematical notation is also noteworthy. His symbolic representation of the chessboard and the knight's moves demonstrates his appreciation for the power of notation in simplifying and clarifying mathematical ideas. Modern mathematics relies heavily on symbolic notation, which allows mathematicians to express complex ideas concisely and precisely. Vandermonde's work reflects this broader trend in the development of mathematical notation. Vandermonde's remarks assert less problems their situation stands as a significant, if often overlooked, contribution to the history of mathematics. His attempt to create an analysis that has foreshadowed the development of topology and graph theory, while the symbolic representation of the knights to exemplify the shift from specific problem solving to the development of general analytical tools. His work reflects a deep appreciation for the power of abstraction and the importance of notation in simplifying and clarifying mathematical ideas. He sought to create a calculus of positions, a way to analyze spatial relationships independently of metric considerations. This ambition aligns with the broader goals of topology and graph theory, which seek to understand the fundamental properties of space and networks. His work on determinants and his early foray into topology showcase his capacity for profound mathematical insight. However, Vandermonde's mathematical career was surprisingly brief, spanning only a few years and resulting in a limited number of publications. This raises a question: why did a mathematician of such apparent talent have such a short and seemingly incomplete mathematical career? The answer requires a shift in perspective, moving beyond the confines of his published papers to consider his broader intellectual and professional life. The subsequent part will delve into the so-called Vandermonde paradox, reconciling Vandermonde the foundational mathematician with Vandermonde the musician, chemist, and revolutionary technocrat. The goal is to present a unified intellectual portrait rather than a fragmented one. Vandermonde's work on determinants and his early foray into topology demonstrate his capacity for profound mathematical insight. His mathematical career, however, spanned only a few years, resulting in a limited number of publications. This naturally leads to the question: why did a mathematician of such apparent talent have such a relatively short mathematical career? Understanding this requires a shift in perspective, moving beyond the confines of his published papers to consider his broader intellectual and professional life. The explanation involves reconciling Vandermonde the foundational mathematician with Vandermonde the musician, chemist, and revolutionary technocrat. The aim is to present a unified intellectual portrait rather than a fragmented one. His career trajectory reveals a consistent application of analytical principles across diverse fields, a hallmark of the Enlightenment ideal. Prior to his mathematical publications, Vandermonde engaged with music theory. In 1078, he presented a work attempting a mathematical foundation for musical harmony. This endeavor, undertaken in collaboration with prominent Enlightenment figures such as Denis Diderot, illustrates a persistent desire to ground aesthetic phenomenon in rational, quantifiable principles. He sought to uncover the underlying mathematical structures governing musical consonance and dissonance, exploring relationships between frequencies and perceived harmony. This pursuit mirrors his later algebraic investigations, where he sought to identify the fundamental structures governing permutations and equations. This early work directly influenced later theorists who sought mathematical models for musical composition, including attempts to codify rules for counterpoint and orchestration using algebraic notation. Following his brief but impactful period of mathematical publication, Vandermonde embarked on a significant career shift towards chemistry and industrial science. This transition, beginning around 1772, saw him aligning himself with the pioneers of the chemical revolution, including Antoine Lavoisier, Claude Louis Berthollet, and Gaspard Maup. He became deeply involved in practical, state-sponsored scientific endeavors. Moving from the abstract realm of algebra to the tangible world of chemical experimentation and industrial processes, Vandermonde's collaboration with Lavoisier highlights his commitment to applying scientific rigor to practical problems. Lavoisier, whose work revolutionized chemistry by establishing quantitative methods and challenging phlogiston theory, provided a model for Vandermonde in applying systematic analysis to complex systems. Berthollet, known for his research on chemical reactions and dyeing processes, further exposed Vandermonde to the practical applications of chemistry in industry. Monge, a prominent mathematician and engineer, played a crucial role in developing descriptive geometry, a field essential for engineering design and manufacturing. Monge's emphasis on visualizing and representing three-dimensional objects mathematically likely influenced Vandermonde's thinking about spatial relationships, potentially contributing to his later interest in topological concepts. His directorship of the Conservatoire National des Arts et Métiers exemplifies his dedication to applying scientific knowledge to practical needs. This institution, established during the French Revolution, aimed to collect, preserve, and disseminate knowledge about tools, machines, and industrial processes. Vandermonde's role involved overseeing the collection of artifacts, organizing educational programs, and promoting technological innovation. This position allowed him to directly influence the development of French industry by fostering a culture of scientific inquiry and technological advancement. Furthermore, Vandermonde played a significant role in the École Normale during the French Revolution. This institution, designed to train teachers in the latest scientific and pedagogical methods, reflected the revolutionary government's commitment to education and enlightenment. As an instructor at the École Normale, Vandermonde contributed to shaping the curriculum and training the next generation of French scientists and educators. His involvement in this project demonstrates his belief in the power of education to transform society. Figures such as Joseph Fourier and Simeon Denis Poisson, who later became prominent mathematicians and physicists, were directly influenced by the educational reforms and scientific ethos promoted by the École Normale during Vandermonde's tenure. Vandermonde also dedicated his technical expertise to improving steel production for armaments, specifically bayonets. This work, undertaken during a period of intense political and military upheaval, highlights his willingness to apply his scientific skills to serve the needs of the French Republic. His contributions to metallurgy involved optimizing the composition and processing of steel to enhance its strength and durability, ensuring the production of reliable weapons for the Revolutionary Army. This practical application of scientific knowledge demonstrates his commitment to the ideals of the Revolution and his belief in the importance of technology for national defense. Vandermonde's career path, therefore, represents a fulfillment of the Enlightenment ideal rather than an abandonment of mathematics. He viewed mathematics, chemistry, and industrial science as interconnected aspects of a unified enterprise aimed at human progress. He addressed foundational problems in mathematics, subsequently applying that same rigorous, structural thinking to tangible problems in science and statecraft. This holistic approach reflects a deep-seated belief in the power of reason and scientific inquiry to improve the human condition. His work in music theory, predating his mathematical publications, showcases a similar impulse to uncover underlying structures and apply rational principles to diverse domains. This early engagement with music, followed by his mathematical investigations and subsequent involvement in chemistry and industrial science, reveals a consistent intellectual thread running throughout his career. He saw these fields as complementary, each offering unique perspectives on the fundamental principles governing the world. The institutional framework of French technical education and the curriculum of the École Normale were directly shaped by Vandermonde's contributions. His efforts to promote scientific literacy and technological innovation had a lasting impact on the development of French science and industry. The École Normale, in particular, served as a breeding ground for future generations of scientists who would build upon the foundations laid by Vandermonde and his colleagues. This legacy extends to figures like Fourier and Poisson, whose work in mathematics and physics was deeply influenced by the educational reforms and scientific ethos promoted by Vandermonde. Therefore, Vandermonde's transition from mathematics to chemistry and industrial science should be understood as a natural progression rather than a deviation from his intellectual pursuits. He saw these fields as interconnected, each offering opportunities to apply his analytical skills and contribute to human progress. His career exemplifies the Enlightenment ideal of applying reason and scientific inquiry to solve practical problems and improve society. The next part will delve into a concluding synthesis of Vandermonde's true legacy, directly addressing the famous misattribution that has often defined him and offering a powerful final assessment. The intellectual ferment of the French Revolution, with its emphasis on reason and progress, propelled Vandermonde into the realm of chemistry and industrial science. His transition should be viewed as a broadening of his intellectual horizons, a natural extension of his analytical skills to new domains. He perceived a deep interconnectedness between mathematics, chemistry, and the burgeoning industrial sector, each offering unique opportunities to apply his rigorous thinking and contribute to societal advancement. His career, in this light, embodies the Enlightenment ideal of employing reason and scientific inquiry to address practical challenges and improve the human condition. A curious twist of fate has inextricably linked Vandermonde's name to an object he never conceived of, the Vandermonde matrix. This matrix and its determinant are cornerstones of polynomial interpolation and signal processing, appearing in countless applications from computer graphics to data analysis. Yet, a thorough examination of Vandermonde's published works reveals no explicit mention of this specific matrix or its determinantal properties. The misattribution, likely originating in the 19th century, presents a historical irony. It has simultaneously amplified Vandermonde's fame, associating him with a readily applicable formula, while paradoxically obscuring his deeper, more transformative conceptual contributions. Vandermonde's true genius resided not in the creation of specific formulas, but in instigating profound conceptual shifts within mathematics. He catalyzed a move from a focus on isolated problem solving to a more holistic analysis of underlying mathematical structures. This transition, though subtle, had far-reaching consequences, laying the groundwork for entire branches of modern mathematics. In the realm of algebra, Vandermonde stands as a pioneer in the study of permutation structures. His investigations into the symmetries of algebraic equations, particularly his work on solving polynomial equations by radicals, foreshadowed the development of Galois theory. While he did not explicitly formulate the concept of a group, his meticulous analysis of how routes of polynomials are permuted under algebraic operations provided crucial insights that later mathematicians, notably Évariste Galois, would formalize into the powerful machinery of group theory. Specifically, Vandermonde meticulously examined the behavior of expressions involving routes of equations when those routes were interchanged. This painstaking analysis of invariants under permutation directly influenced Lagrange's work on the same topic, which in turn served as a critical stepping stone for Galois' revolutionary ideas. Lagrange, in his Reflections sur la résolution algébrique des equations, explicitly built upon Vandermonde's earlier work, acknowledging its importance in understanding the structure of polynomial equations. Galois, deeply influenced by both Lagrange and Cauchy, ultimately generalized these ideas into the framework of group theory, a cornerstone of modern algebra. Vandermonde's impact extended to linear algebra, where he played a crucial role in transforming the determinant from a mere computational tool into an abstract, symbolic system. Before Vandermonde, determinants were primarily viewed as a means to solve systems of linear equations. Vandermonde, however, began to explore the inherent properties of determinants themselves, independent of their application to equation solving. He investigated the behavior of determinants under various transformations, recognizing their fundamental algebraic structure. This shift in perspective paved the way for the development of abstract linear algebra, where determinants are studied as objects in their own right, with rich connections to concepts such as eigenvalues, eigenvectors, and matrix invertibility. Cauchy, building upon Vandermonde's work, provided a more rigorous and systematic treatment of determinants, solidifying their place as fundamental objects in linear algebra. Cayley, in turn, further developed the theory of matrices, drawing heavily on the earlier work of Vandermonde and Cauchy, and establishing the foundations for modern matrix algebra. Furthermore, Vandermonde's work in combinatorics initiated the algebraization of position and connectivity, prefiguring concepts that would later blossom into the field of topology. His investigations into the Knight's tour problem, for example, demonstrated an interest in the abstract relationships between points on a grid, irrespective of their specific coordinates. He sought to understand the underlying structure of the Knight's movements, rather than simply finding a specific solution. This focus on connectivity and relationships between objects foreshadowed the topological perspective, which emphasizes the properties of spaces that are invariant under continuous deformations. While Vandermonde did not explicitly develop the language of topology, his work on combinatorial problems hinted at the importance of abstract relationships and connectivity, ideas that would later be formalized by mathematicians such as Poincaré and Riemann. Euler's earlier work on the Königsberg bridge problem, which focused on the connectivity of the bridges rather than their specific lengths or locations, undoubtedly influenced Vandermonde's thinking. Poincaré, in his development of algebraic topology, explicitly built upon these earlier combinatorial ideas, using algebraic tools to study the connectivity of topological spaces. Vandermonde stands as a pivotal, yet often underappreciated, transitional figure in the history of mathematics. His work contains the intellectual DNA of group theory, abstract linear algebra, and topology, three cornerstones of modern mathematics. His career, spanning from musician to mathematician to revolutionary technocrat, embodies the Enlightenment's ideal fusion of abstract reason and practical application. He sought to apply his analytical skills to a wide range of problems, from the theoretical intricacies of algebra to the practical challenges of industrial production. Understanding Vandermonde's genuine contributions is more than a matter of historical correction. It allows us to witness the very moment when the 18th century's mathematics of calculation began its transformation into the 19th century's mathematics of structure. He represents a crucial bridge between the era of Euler and Lagrange, focused on explicit formulas and computational techniques, and the era of Galois, Cauchy, and Riemann, characterized by abstract concepts and structural analysis. By recognizing Vandermonde's pivotal role, we gain a deeper appreciation for the evolution of mathematical thought and the interconnectedness of seemingly disparate fields. His legacy lies not in a single formula, but in a fundamental shift in perspective, a move towards a more abstract, structural, and ultimately more powerful understanding of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.